Welcome to this lecture where I would like to discuss some of the performance and software engineering aspects that revolve around automatic memory management and in particular garbage collection. So garbage collection is not new. Developers have spent decades developing different garbage collection algorithms, tuning them and optimizing them. As one data point, the 11th edition of Java shipped with 4 different collectors. Just 2 years ago, a 5th collector called ZGC was added in 2018. These collectors or collection algorithms differ in many characteristics in terms of the program throughput they enable. That is, to what degree do they slow down the user program that is executing, how much additional memory they need, and what their GC throughput is. That is how much garbage they can collect in a given amount of time. Their scalability. Here, scalability means whether those algorithms work well on small as well as large heaps, and so on. There are many different characteristics that are important when it comes to garbage collection. But what is also important is to have a good understanding of your workload so that you can estimate what the impact of your workload is on the garbage collection performance, and if needed, tune the garbage collector or recognize deficiencies in the workload in the program that you are writing. In fact, that is a very frequent task that many developers who work in managed languages have to do in their professional life. This includes both Java, but also JavaScript, and today, in fact, more often JavaScript than Java. So I'd like to tell you a little about how garbage collectors work and how this may impact the performance that you see. So in the last lecture, I talked about mark and sweep as a way of thinking about garbage collection, whereby the reachability graph is used and the garbage collector performs a mark phase where it traverses the reachability graph, finds the objects that are reachable, marks them, and then sweeps or frees the rest. Well, this was a bit of an oversimplification. Real-world collectors are, in fact, a lot smarter than that. And one of the things that they can do is they can compact the heap. Now, an explicit memory allocator, that malloc and free, cannot do that. It cannot move an object from one place in the heap to another. But a garbage collector designed for a managed language such as Java can do that because it has knowledge of where in the object graph pointers to an object are stored. And so if the object is moved, it is possible for it to update those pointers so that the user program will still work even when objects have been moved. Now, moving objects in this way allows another trick. Objects now can be evacuated, also referred to as scavenged, from the region of the heap where they were originally allocated. The idea is to place objects into some area and then find those that are reachable or live, take them and move them into another area. If you do that, then all objects that have not been moved in this way are garbage, and it is more efficient to reclaim all of them at once because they are in one contiguous area of the heap. So this is the idea behind a compacting collector. Now, given this fact, how can we model the cost of garbage collection? Well, first, there's the cost of marking itself. And in the case of compacting collectors, any object that is marked is reachable, and therefore it may have to be evacuated or copied. This cost is proportional to the size of the live objects in the area that is being marked. Okay? And the size of the objects that have to be evacuated if an object has to be evacuated. So this is a characteristic that depends on how many objects your application keeps around, but it also depends on exactly when garbage collection takes place, because the size of the live heap may change. And the second cost would be the cost of sweeping. Now, if sweeping were implemented naively by calling free on each object, then this cost would be proportional to the amount of garbage your application generates. But in the presence of compacting and evacuation, in theory at least, this cost would be constant. It would not depend on how much garbage your program generates, because those areas that have only unreachable objects left in them can be reclaimed more efficiently. However, there's one issue in practice, which is that in languages that use garbage collection, Java for example, there's a guarantee that a newly allocated object is properly initialized to be all zeros. Well, the runtime system has to do that somehow. And in fact, this is a cost that is typically um, ascribed to the garbage collector. So the swept memory that is reclaimed still has to be zeroed out. And in fact, studies have shown that this can be quite a significant cost that is proportional to the amount of garbage that is produced. Okay, so we have two costs, cost of marking, the cost of sweeping. Um, You may ask the question, how can we model the behavior of an application with respect to its memory allocation? One way to do that is to use a so-called memory allocation profile. Okay, so this is shown here on this graph. We can think of on the x-axis we may have time. So this could either be real time, but it could also be measured in terms of the number of bytes that the allocation is allocating. And then we can look at two curves which respect at the cumulative amount of memory that is on the heap. So we can, for one, look at how the size of the live heap may change over time, and then the size of the total size of the allocated objects. So that is a monotonically increasing function as far as the application is concerned. So now, what would happen if an application runs and it allocates objects, it produces an amount of garbage? Well, this cannot go on indefinitely. So at some point, a limit would be reached, right? Like any resource, memory is finite. So we like to think of it as the heap limit. So in a garbage collector or a system using garbage collection needs to make a decision as to how much memory it wishes to use. So typically there is a heap limit, and if that heap limit is reached, or if it gets near to that, garbage collection would occur. What I showed on this slide here is the general case, right? So applications could really have any pattern in terms of how their live heap changes. It is very application specific. But very often a more simplified model is being used. And in this model, we assume that the application allocates memory at a constant rate. Maybe that may change over in different phases of the application, but at a given point in time, we say that maybe the allocation allocates at an allocation rate. The live heap size of the application, again, it can vary between applications, but a simple model is to assume that when the application starts up, the live heap size will increase up to some steady state, and then let's say it will stay at this state. So if this is our model, let's see how the application performance may be affected by the choice of the live heap size. To that end, I've created a small program that I would like to share with you and show its effect. So this program, I call it large live heap, and it is just a few lines of code. It takes two command line arguments, the number of live objects and the number of allocations. And then it will allocate a two-dimensional array of bytes. So in Java, two-dimensional arrays, the first dimension is an array of references, and the second dimension are just the references themselves. And then in a loop, I will perform a certain number of allocations. And for each allocation, I'm going to allocate a large array of bytes, here in this case 100,000 bytes. And I'm going to write this into one of the references in this array, but I'm going to mod this with the number of live references so that the first is placed in the first one, second, third, and so on. But if the number of allocation is larger than the number of num live, some of the ones that are already there are being overwritten. In fact, I would like to show the effect of this using Philip Guer's Java heap visualization tool that I used in the lecture on garbage collection. So here I just used 3 allocations in this case, and sorry, not 3 allocations, 12 allocations, and I'm keeping the 3 most recent ones alive. And to visualize it, I'm also going to put the number of the allocation inside the the first byte. Okay, so let's take a look at what this would, what the behavior would be. So a program would start. We would allocate um, the array of references to byte arrays. In this case, 3 of them shown here. And then we start allocating. Let's say, okay, we're going to allocate one array. I'm only making these arrays smaller here, only 10 bytes. And so the first array is allocated and is stored in the first entry. And the next one is allocated and is stored in the next entry. And the third one goes into the third entry. So now what happens if the fourth one is allocated? So it's being allocated. It has the value 3 with the fourth one written to it. But then it will be stored in this array. And what happened to the previous one? Well, it's no longer shown here. Well, this is one that would then become garbage. And so if I keep doing that, you can see that a total of 12 arrays is being allocated, but only the 3 most recent ones are being stored. So now let's look at the behavior of this program if we chose some larger numbers. Okay, so I have here the number of live. I can specify the number of allocations. I can specify it, and I'm going to run this program. So let me compile this. And so what do I have? And currently I'm using Java 10 on this computer. So let's see. I'm going to use the time command, and I'm going to try out how long it would take if I did 1,000, I kept 1,000 alive, and I do 10,000 allocations. I do this, and this would take, in this case, about half a second. Let's say it takes half a second. Okay. So what if I change the maximum live heap size? In Java, you can do this with the flag -mx, and you can specify it. For example, I could say 1 gigabyte. Okay. So if I do that, in this case, well, about the same time. Let's see if I make it smaller. So first of all, let's see what would happen if I made it really small. Let's say 64 megabytes. Yeah. So in this case, I would run it, and I get an out-of-memory error. The out-of-memory error is thrown because it is not possible to keep around 1,000 byte arrays of length 100,000 in this case on the heap. The heap is just too small. The heap limit is set too small. So let me increase it. Let's say 128. So I did this, the program ran, but let's look at the time. Okay, so first of all, the program took more than twice as long. And during that time, by the way, it used 5 seconds of user time. The reason for that is that Java's garbage collector, one that's being used here, G1 collector, is in fact multi-threaded. So garbage collection took place on other cores and used CPU time. But it still was a slowdown of a factor of 2 compared to the larger heap size. So what would happen if I restricted the heap size even more? So for example, if I restricted the heap size to 110 megabyte, now we see this program running for 3.2 seconds, taking up 13.4 seconds. Let's see if I can go even smaller. If I set the heap limit to 105 megabytes for this particular workload, we would see it run for 5 seconds. It's possible in Java to specify verbose GC to see what the system is doing. What we can see here is a fair amount of garbage collection activity going on. This effect is known as GC thrashing. That is a performance degradation when the maximum heap size is too small relative to the live heap size. I'd like to show a visualization that was created by one of my former PhD students, Shahruz Fezabadi. So if you think of the execution of a program as consisting of basically allocation at some rate shown here up to when a garbage collection is triggered, then the garbage collection would take some time, and but it would free up some garbage, and then more allocation would again increase the number of objects allocated on the heap until the garbage collection would take place again. And we see this pattern that is shown here. Now let's look at what would happen if the um, if we increase the heap limit. Okay, so if we did that, we would have to garbage collect less often, right? If we increase it even more, even less often, and we see that the overall execution time of our program would decrease. Okay. In fact, if we were able to use an infinite amount of memory, we may not have to garbage collect at all and would save execution time. This visualization shows this in a somewhat exaggerated and simplified fashion, but the effect is real. That is the trade-off between the size of the heap and the performance of your program. So large live heap sizes tend to increase the frequency of garbage collections, particularly when the JVM approaches the heap limit. The details vary. JVMs have carefully tuned policies when they do garbage collection, and so they try to use heuristics to optimize this process, but the underlying effect is the same. There's a question. So what should that maximum heap size be? Couldn't the virtual machine just ask the operating system for more memory? I'd explained that Java virtual machines and other virtual machines typically run on top of an operating system that supports virtual memory. So it could ask for more memory. This is a trade-off here. Um, in Java, it uses some default settings that are heuristics, and you can change them with the -x mx switch if you're willing to use more memory. But this may have an adverse impact on other uses of memory on your system. Okay? So what is a good amount of memory to budget in order to achieve tolerable garbage collection overhead? Traditional wisdom had it that one should budget between 150 to 250% the size of the live heap to stay within an acceptable performance slowdown. However, there are past studies, for example, a study in 2005 by Hertz and others, found different results. According to this study, um, many garbage collectors at that time needed up to 3 times the live heap size to achieve only 17% of performance degradation when compared to an idealized program that did malloc and free. And with only giving twice as much, they were in fact 70% slower, and they needed 5 times the size before they outperformed malloc because of the effect that I showed earlier. Now this is something that is being actively developed, and so with more recent collectors, we may see better effects here, but nevertheless, the it is still true today that garbage collected languages do require a fair amount of additional memory compared to what the application needs in order to perform well. So this is one thing to remember. Look at the size of your live heap and see if it approaches the maximum heap size, because this can yield this particular effect. It can also lead other effects that I'll be talking about shortly. So before doing that, let me talk about the generational hypotheses. So an observation is that not all objects in a program are created equal. Some objects are being allocated and they become garbage shortly after. Other objects are being allocated and their lifetime is the entire lifetime of the program. They're long-lived. The generational hypothesis says that most objects die young in this case. So what that means is that they do not survive many collections. So this is shown here on this graph, which is taken from the Java hotspot documentation, and it shows on the x-axis the number of bytes allocated as a measure of time, and then here the number of bytes that survive. Okay. So because of this, some garbage collectors, including the GC1 collector that is the default in Java as of today, use different generations. So when an object is allocated, it goes into the first generation, and it goes by different names. Nursery is one, or something called the Eden space. And this space is collected more frequently in a so-called minor collection. Okay, the idea is that in this collection, most of the objects that were found will be garbage. Maybe a few will have to be evacuated and placed into an older generation. The objects in the older generation are said to be tenured as well. In systems exploiting generational collections, it is now necessary to coordinate between the user program that may change the object graph, the reachability graph, and the garbage collector. The user program is referred to as the mutator because it mutates the reachability graph as it executes and creates new connections between objects. Specifically, in order to be able to garbage collect the nursery separately from the remaining parts of the heap, it is necessary to treat pointers into Eden space as roots during that collection so that it's recognized that they are alive and that they won't be freed. So if there's an assignment where an object that is outside the Eden space points into the Eden space through a field, then the collector needs to be informed that this object inside the Eden space needs to be kept alive and eventually evacuated. So this is a so-called write barrier because it is an action that the mutator has to perform when it, in this case, writes to an object, when it sets a field in an object. What this example shows is that in order to implement this type of collector, it is necessary to have some coordination from the mutator. Now, coordination here in this case means that something else needs to be performed beside what the application programmer wanted. Now, this is done by integrating it with either the compiler, but in Java, for example, with the just-in-time compiler, the hotspot compiler that generates code that is executing. In fact, in modern systems, the just-in-time compiler is tightly integrated with the garbage collector. This is not what I just showed is not the only example where an interaction between the mutator and the garbage collector takes place. In general, you can imagine that the reachability graph changes rapidly as an application executes. New objects are being allocated, new connections are being created, new pointers are being updated, overwritten, so some connections are being removed, some edges are being removed. There are three major approaches when it comes to coordinating the mutator threads and the garbage collector. So for all of these, it's important that a situation must be avoided where the garbage collector may inadvertently miss the last pointer to an object that keeps that object alive and then erroneously deallocates this object. Okay, so this is something that a correct garbage collector must avoid. Note that the opposite scenario where an object has become unreachable, but maybe the garbage collector doesn't realize it or doesn't realize it quite at the point it happens, is just a performance issue, not a correctness issue. So what are these approaches? Okay, so the oldest and traditional approach is called stop the world. That says when it's garbage collection time, we stop all mutating threads, do garbage collection, and then restart them. This has the advantage that the garbage collector can do its work and doesn't need to worry about concurrent changes by those mutators. But it also has a disadvantage, which is that it can lead to so-called GC pauses, where the application just stops for garbage collection and essentially takes a break. And this is something that has been observed in systems and the accompanying adverse impact on performance, and also here in particularly the unpredictability of when this happens. This is also what makes garbage collection challenging in real-time environments when when guarantees about the latency, the time it takes for tasks to execute are required. And we would not want side effects by triggering a GC pause in the allocator just because the application happens to allocate some memory. So what are some alternative approaches? One approach is called incremental collection. So here the idea is to do a small amount of GC, maybe a small amount of marking concurrently with allocating objects. Okay. So while allocating objects, in this case, this could be done in the context of the mutator thread rather than having a separate, rather than signaling a separate thread to do this amount. So incremental collection is an approach to do that, although many of the collectors that are in wide use today no longer use an incremental approach. Instead, what they do use is a concurrent or parallel collection approach. In those cases, the garbage collector runs in one or more separate threads. And it also has the advantage that it allows us to use multiple cores, which are now ubiquitous on many computers, even embedded systems. Systems that exploit concurrent or parallel collection need to synchronize with the mutating threads. I showed one example already, the write barriers that generational collectors use to make sure that they don't inadvertently free objects in the Eden space that are kept alive by the older generation. But there are many different variations of this. So for example, sometimes it also makes sense to inform in the other direction and to make it so that a garbage collector is able to move an object and do so safely in a way that a mutator would notice. Okay, so when a mutator, for example, retrieves a reference to an object, then a load barrier could be used to stop that mutator in the case that the object has been moved. So let me briefly talk about um, the garbage collectors that are currently used in Java. So Java, in fact, has four, and the default has changed over time, different versions of Java. The G1GC became the default collector somewhere, I would say, maybe about in the 2010 to 2015 timeframe. The ZGC or ZGC, as the developers would call it, it's been developed in the last couple of years. It's currently in the experimental stage and might become the default garbage collector in the future. ZGC is interestingly, it's a single generation collector. And the reason is that it can evacuate objects while the mutator is running. Okay? So in this case, it actually doesn't need to have multiple generations. This comes at a cost, these load barriers, which the developers of GCC were able to highly optimize. So the claimed advantage here is to have, for this collector, to have very low latency. In fact, the mutator may only stop during the root scanning. So this is when the roots, like the local variables on different threads stacks, are being identified. If you'd like to learn more about this, I recommend two blog posts by Mike Hearn, one from 2016 where he discusses some of the claims that the developers of the Go garbage collectors made, and then an update in 2019 that discusses ZGC as well as the Shenandoah collector, which is also a recently developed collector. I would like to point out the discussion, the relationship between live heap size and maximum amount of memory one is willing to give to the heap. It remains with all these collectors one of the key performance influencing factors. Okay? In fact, the developers of ZGC mentioned this in a YouTube video that you can watch, as the primary tuning knob for their collectors. For the G1GC collector, one of the tuning factors there was the size of the nursery, the size of the Eden space. So depending on the behavior of the allocation, this may be something to tune there as well. Let's talk about this from the programmer's perspective. Okay, so I said at the beginning of this lecture that many of you will be spending a fair amount of time in garbage collected managed languages doing programming there, and you will be encountering situations where your program runs out of memory. So then what do you do? So first of all, how do you know this? In Java, typically you would see it that an out of memory error is shown, like I showed earlier in my demo. So first, the very first thing is that's important is to understand what has happened when an out of memory error is shown. Sometimes people think, oh, Java is a garbage collected language. How can it run out of memory? Did the garbage collector fail somehow? Well, an out of memory error is shown when the live heap size exceeds the memory limit. In other words, there is not enough memory for the JVM to keep all the objects alive that are reachable, okay, even after it has collected all the garbage. Okay. This is what an out of memory error means. Now, how could that happen? Typically for three reasons, one of three reasons. Well, the first one is that it may just be that your heap size is too low. Okay, so if your problem asks you to, for example, allocate a certain number of arrays of a certain size and your overall heap size limit is too low, it may just be plain impossible to keep all these objects on the heap. But there are two other reasons that can occur. Those are leaks and bloat, which I'll be talking about. The second phenomenon that you may see is that your program's performance degrades because a lot of time is spent in GC. So this could again be for two reasons. One is churn, and the second one is this lack of headroom. That is, the size of the live heap is too close to the heap size limit, and that is the effect that I had shown earlier in Charus's animation. Okay, so let's talk about these issues. Okay, the first one is that of leaks. Okay, so a leak is a reachable object that is on the live heap, part of the live heap. There is a sequence of edges leading to it from one or more root, but the program in fact will not access this object in the future. It could, but it won't. And how do we know this? Because this is something the programmer has to tell. Oh, they say, well, this is an object that is perhaps stored in a hash map. But in fact, the key is no longer accessible, right? So there is no possible execution of this program where this object would be looked up. Okay? This is a decision that is related to the semantics of the program, something that you as the programmer would have to decide. You can use tools, memory analysis tools such as Heap Hero or Eclipse Memory Analyzer that show you a snapshot of a heap at the point in time when it ran out of memory. You can analyze it, but then you as the application programmer have to make the call whether this is in fact a leak. You will see a reachable object, but it would be a leak if and only if you make the call that this particular object in fact will not be accessed in the future. It's in general undecidable, so therefore you have to make this call. So I mentioned items placed in hash maps or other containers. Those are frequent sources of memory leaks. In this case, what you would see is you would see the memory consumption of your program to steadily increase. The size of the live heap would be increasing. Other examples are event handlers that were registered and not unregistered. Those are frequent sources of memory leaks, particularly web applications where the same phenomenon can occur. Callbacks are another one. In JavaScript, for example, callbacks contain so-called closure, that is, they have references to all the objects in their environment, and they keep them alive as far as the garbage collector is concerned. So those are called leaks. Now, there is one defense against leaks, and it's called weak references, but it can be applied only in situations where, in fact, the programmer doesn't know whether something will be accessed in the future, and it's okay to drop it, garbage collect the memory, and recreate it. This would be in the case of caches. So if you implement a cache, you place objects in there opportunistically and optimistically, thinking that they may be accessed in the future, and in fact, this may be possible, but Those objects are then part of your live heap. So if you place too many objects in it, you may run out of memory and increase the size of your live heap. And then it's not clear, are these objects in the cache, are they leaked or not? Weak references can help with this. A weak reference is a reference that is created through a special API in Java. And you as the programmer, you're telling the JVM, okay, this object, if you're short on memory, then it's okay to disregard the edge in the reachability graph and reclaim this object. And the next time I'm trying to access this object, I will learn that this object has been freed and I can reclaim it. So weak references assume that the use of weak references is a conscious decision by the programmer and assume that they understand the trade-off between the maximum heap size and the live heap size. General leaks are objects that programmers inadvertently keep alive when in fact they know that they won't be accessed in the future. So those are leaks. What about bloat? Now it turns out that in Java in particular, a situation can occur where your live heap actually doesn't have any leaks. All the objects that are in there should be in there and will be accessed in the future, but yet you run out of space. And a common cause of this is that the objects that you're allocating just take up too much space because of the way they are implemented. And this is particularly an issue in Java, because in Java, every object is individually allocated on the heap, and everywhere it is referred to through a reference. So unlike in C, where we can embed multiple objects in arrays, we can't do that in Java. On top of that, the Java uh, containers implemented in the Java library tend to have a high overhead in terms of storing such objects. For example, just storing an individual item in a hash map may, just in terms of the pointers, may take 24 or 40 bytes. And then add to this for each object the overhead for its header and so on. And you sometimes get a factor of 7 or 10 beyond the data that you're storing just for these container data structures. Boxed integers, those are capital integers with capital I or capital L for long, are a particular source of this overhead. There is a 2011 paper by Chi and others that analyzes this. This is the paper that I added to the references here. So this is referred to as bloat. Okay? And the strategies to reduce bloat are, for example, to avoid, for example, boxed integers. If actual primitive integers, lowercase int, can be used, that is much preferred. Memory analysis tools help with both leaks and bloat because they can show you how many actual bytes are being taken up by an object in a part of the heap. Besides, so leak and bloat tend to increase the maximum live heap size and may lead to situations where you eventually run out of memory. Churn is a more subtle phenomenon where the overall allocation rate of your application is too high. So the application allocates objects, they're short-lived, so they have to be reclaimed, triggering frequent garbage collection. This is something that you want to avoid in general as well. It's particularly important on resource-constrained devices. For example, one of the guidelines for Android developments is specifically to avoid this memory churn. This may take the form of pre-allocating objects, keeping objects around and reusing them. In many cases, this is at odds with the object-oriented programming style that we like to adopt in Java, where we pretend that allocating an object is free and that the garbage collector will just take care of things, and to adapt a style that is more similar to the style that we would be programming in the C language in particular. This is called churn. That's so far talked a lot about Java and other type-safe managed languages. It is, however, also possible to apply garbage collection in C and C++, and in fact, there is a long history of doing so. Now, one of the issues that occurs here is that we may not have exact information as to where pointers are stored. This is unlike the collectors that are used in Java and C#. Those collectors are said to be precise garbage collectors. Here, precision means that they have precise information where pointers are stored. They know for every single heap object what the fields are, what the types are. And in Java, for example, if the type of a field is an int, we know that there can't be a reference stored because the language is type safe, the compiler enforces this. Moreover, a precise collector has exact knowledge of the stack frames. It knows exactly where local variables are being stored or whether they are kept in a register, for example. So with such precise knowledge, a garbage collector can do a better job at identifying which objects are reachable. Now, a conservative collector, by contrast, does not make the assumption that it knows all the places where pointers are stored. Instead, it looks at those locations in memory on the stack frames of running threads or within allocated objects or blocks of memory, and it looks at them and assumes that anything in there that could be a pointer is one. So if it sees a 4-byte value or 8-byte value, depending on the architecture, that points to that has a value that could constitute an address, it assumes it's pointing to an object and it keeps that object alive conservatively. So it may keep some objects alive that are not reachable, but it is compatible with languages such as C or C++, where we do not have precise information about what type is stored where. Hans Böhm's conservative garbage collector is one of the first systems to use this idea. It's been around for a long time. And as part of the C++ 11 standardization effort, he led a group that defined precise conditions for compilers to avoid inadvertently producing code that would trip up such a garbage collector. So the compiler still doesn't have to produce information about exactly where things are, but it must avoid producing code that would lead even a conservative garbage collector to miss pointers. Okay, an example here are pointers inside objects, right? So this is something where the garbage collector would see a pointer, but it wouldn't point to an object that was allocated. And situations like this need to be reasoned about. And that has been done as part of the C++ 11 standard. So conservative garbage collectors are certainly a viable alternative to explicit memory management, even in programs using the C or C++ language. And I urge you to try them out. Lastly, I would like to mention Valgrind's leak detection algorithm, which I've seen a number of you use when you run Valgrind. At the end, it tells you this many objects are probably lost or definitely lost. So Valgrind uses, in fact, the same idea. It uses the same mechanism that a conservative garbage collector would use. It scans the heap, it follows references found in allocated data blocks and concludes that if those references were followed, then the object that is being pointed to could be accessed. So in essence, it creates what in a language like Java would be a live heap scan. Then it reports if there are any still allocated objects that are not reachable in this way, and it says those are lost. That is a leak, but notice that this is a different type of leak from the one we talked about in Java. This leak that Valgrind flags are objects that are no longer reachable but have not been deallocated. This is the C programmer forgetting to call free. Okay? This is not the leak that we have in Java, where the programmer, first of all, cannot call free, but the programmer made it so that there is a reference to an object, but this is an object that the programmer will not be accessing in the future. If you'd like to learn more about this, here are two references to papers. The first one is the one that describes many situations where in Java the inefficient data structures are being used, where bloat occurs, and how to avoid them. And the second one is the paper that compares the performance of garbage collectors with that of malloc, although it is somewhat older and does not benchmark more recent collectors.